I'm R. Prabha, Assistant Professor in the Department of ECE, SNS College of Technology. In this video, we are going to discuss the topic on wave propagation in lossy dielectrics. So, what is a lossy dielectric? So, it is a medium in which electromagnetic wave, as it propagates and loses power owing to imperfect dielectric. So, in other words, a lossy dielectric is a partially conducting medium. We call it as imperfect dielectric or imperfect conductor, with the conductivity sigma value is equal to not equal to 0, as distinct from lossless dielectric, which is otherwise called as perfect or good dielectric, where the conductivity value sigma is equal to 0. So, this is the difference between lossless and lossy dielectrics. Okay. We'll see the Maxwell's equations for lossy dielectrics. We know there are four Maxwell's equations which form the foundation of existence of electromagnetic waves. And James Clerk Maxwell have formed the four mathematical equations, two curl equations and two dot equations. And the first equation del dot E is equal to 0 for lossy dielectric, del dot H also 0, and del cross E is equal to minus j omega mu H, and del cross H is equal to sigma plus j omega epsilon into E. And Maxwell's equations for lossy dielectrics. Now we are taking the curl of both sides of Maxwell's equation, and del cross E is equal to minus j omega mu into del cross H. Now we are applying the vector identity del cross A is equal to del into del dot A minus del square A, and this del dot E is equal to 0, and so this equation becomes minus del square E is equal to minus j omega mu sigma plus j omega epsilon into Es. So finally we can write del square Es minus gamma squared Es equal to 0. And here the gamma squared is nothing but the value of propagation constant, the whole square, and it is equal to j omega mu sigma plus j omega epsilon. And here this mu is the permeability, omega is angular frequency, sigma conductivity, epsilon is called permittivity. And in reciprocal meters, gamma is called, and it is the propagation constant of the medium. And Maxwell's equations for lossy dielectric, in a similar procedure we can find for electric magnetic field as del squared Hs minus gamma squared Hs equal to 0. So here gamma is the complex quantity. We know gamma is the propagation constant. It is equal to the real part alpha, the attenuation constant, plus j into the imaginary constant beta, called as phase constant. And now the Maxwell's equation for lossy dielectrics, it has the value of alpha and beta. Since the lossy dielectric is imperfect dielectric, so it has the alpha attenuation value. The reason is the wave has the possibility of attenuating. Attenuation means reducing amplitude while propagating. So alpha value is equal to omega root of mu epsilon by 2 multiplied by the square root of 1 plus sigma by omega epsilon the whole square minus 1, and beta value is equal to omega root of mu epsilon by 2 multiplied by root of 1 plus sigma by omega epsilon the whole square plus 1. The difference between alpha and beta value is inside the second radical we have a minus symbol instead of plus symbol in beta. And now for lossy dielectrics, the wave propagation will be like this. The wave amplitude initially it is high and it start decreasing. The wave is dampening. The reason is it has alpha value. When the wave electromagnetic wave is propagating through lossy dielectric, it gets attenuated so that its amplitude decreases. And the wave propagation along AZ, it decreases or attenuated by a factor e power minus alpha Z, and alpha is known as the attenuation constant, or it is also called as attenuation coefficient of the given medium, and it's a measure of spatial rate of decay of decibels per meter dB per m, and attenuation of 1 ampere denotes a reduction of e power minus 1 of its original amplitude value, whereas an increase of 1 ampere indicates the increase of by a factor e, and 1 ampere is equal to 20 log 10 e, 58.686 decibels. And assessment question. So a problem is given: a lossless dielectric has an intrinsic impedance of 200 angle 30-degree ohms at a particular radiant frequency V. If at that frequency the plane waves propagating through the dielectric has the magnetic field component H is equal to 10 into e power minus alpha z cos omega t minus 1 by 2x ay ampere per meter. In the problem, they are asked to find out the value of the electric field E and the attenuation constant alpha. So if you observe the parameters given in the assessment problem, intrinsic impedance eta value is given 200 angle 30-degree ohms, and the amplitude of magnetic field H is also given 10 power 10 into e power minus alpha x cos omega t minus 1 by 2 x ay amperes per meter. Here ay represents the wave is propagating in uh, other direction other than this y, because magnetic field is in the y direction. So electric field must be in x direction, and the wave propagation must be in z direction, because both electric field, magnetic field and the direction of wave propagation all are perpendicular and perpendicular to one another. So if eta value is equal to E by H, so here eta is given, H is given, so we can easily find out the value of electric field E. And next is we can easily calculate the alpha value from the formula we have seen in this example. References. Thank you.